So today we are going to talk about the elimination reactions. So here we will be talking about E1 and E2 and then E1CB. So among these three, all these three elimination reactions are very important. So what are the essential conditions for elimination? Essential condition for elimination reactions. The first thing is the nucleophile should be a strong base. This is the first condition. And the second condition, the beta carbon should have one hydrogen. So if these two conditions are there, elimination is preferable. If the nucleophile is a weak base or a neutral base, then here the substitution is preferable over elimination. Okay, if nucleophile is a weak base or neutral base, weak base means more weak, we can say that neutral base. Okay, so weak base is also even is possible in case of weak base, so we can say neutral bases. If a nucleophile is a neutral base, in that cases substitution is preferable over elimination reactions, and these two conditions we have to remember. And where we doesn't have any beta hydrogen, like this compound, the carbon which is having a leaving group, that is alpha, and next to that this is beta. So as we can see here, there is no beta hydrogens. Because of that reason, this will not undergo elimination reactions. Okay, and many examples are there, like we can take this example also. Here also there is no beta hydrogen, here no hydrogen, so because of that this elimination will not take place. And we can take this example also, R. So this is alpha and this is beta. So if there is no beta carbon, so then elimination is not possible. And then first we'll talk about the E1 elimination reactions. So E1 elimination reactions mainly depends upon the stability of carbocation. So if is there any stability factors, like I will be writing some examples here. So this is the one, and this type of compounds, and this is X. Okay, this is OMe and X. And if we see in these compounds, so what's happening here, this is forming a stable carbocation. The carbocation is further stabilizing by the ring. Okay, and here also this is further stabilizing by the conjugation, and here it's further stabilizing by the heteroatom. So the stable carbocations undergoes even elimination reactions. So one more thing here we need to remember that, so the compounds which undergoing E1 elimination, they can also undergo E2 elimination. Okay, but the compounds which are undergoing E2 elimination, they can't undergo E1 elimination. Okay, this all depends upon the base. Okay, so what is the base effect, that I will be explaining later once it is done. So as of now I am going to explain what is E1 elimination and what is the E2 elimination reactions. And E2 elimination is like it's a like both the abstraction of base as well, and also abstraction of base and elimination of elimination of leaving group. So both take simultaneously. Okay, so in case of E1, first so what is the mechanism for E1? The leaving group eliminates first plus, and in this step we have a base, so they will get a alkene here. and the rate of reaction here, it's only depends upon the concentration of substrate, because the rate determining step is this step. Okay, the first step is a slow step, this is a rate determining step. So because here no base we are using, in the second step we are using base, so because of that the rate depends upon the only on the concentration of substrate. Whereas in case of V2 elimination, so rate depends upon the both substrate as well as concentration of base. Okay, so this is the brief introduction about the elimination reactions. So now we'll go what is the effect of basicity and what is the effect of nucleophilicity. These are very very important, and living group and temperature, those things. The first one is effect of basicity. So first one is a weak base, strong base. Second one is strong base. When we take a weak base, this will preferably under weak bases even elimination is preferable. Under the strong base, E2 elimination is preferable. Why for weak base even strong base E2? So as we see in case of alkyl halides in an even mechanism, the first step is the elimination of a leaving group, and the second step is the abstraction of proton. Okay, and this is the slow step and this is the fast step. Okay, so anyway this step is very fast, so for that we no need to use a strong base. Okay, so weak base is sufficient for this. Okay, and for even elimination weak base, under the weak base even elimination takes place. For strong base E2 elimination takes place. Why E2 requires a strong base? So in case of E2, it is a concerted mechanism. That means elimination of leaving group and proton abstraction both takes place in the same step. So because of that reason, in order to make rate of reaction faster, we have to use a high concentration of base, or like we can say that we have to use a strong base. And because here in the first step itself we are removing the proton removing the proton. So because of that reason we need a strong base for E2 elimination. Okay, for even elimination weak base, for E2 elimination strong base. And here we'll see some example. Chlorine. So here we have a in the presence of ethanol, and also same example in the presence of ethoxide. So the question is what kind of reactions are favorable in the compound A and B? So here we have to see the base. Okay, so we know that if a nucleophile is a strong base, so there elimination is favorable over substitution, right? So compared to ethoxide and ethoxide in ethanol, we know that ethoxide is a conjugate base of ethanol. Okay, so this is a strong base. So that means ethanol is a weak acid, right? So since this is a strong base, ethoxide is strong base, here elimination reaction is favorable, and since this is not a strong base, like here substitution will be favorable. Okay, the question is what kind of reactions are possible in these two compounds when we have ethanol and ethoxide is a question. So ethoxide is a strong base because ethoxide is a conjugate base of ethanol, and since it is a strong base, here elimination reaction is favorable, whereas in case of ethanol, substitution reaction is favorable. Another thing, when we have a OH in the acidic medium, what will happen? This lone pair abstract this hydrogen, then this gets converted into OH2. Now the elimination of water takes place, and this will be positive charge. Okay, so here this will be alpha and this will be beta. So this hydrogen goes like this, means in the presence of base the abstraction of hydrogen takes place. This is the final product, and the question is whether this reaction here in this step, here base, right, in this step, whether it's required a weak base or strong base. So this is the question. So just remember, the compounds which are having a hydroxyl group containing compounds undergoes reaction through the only E1 mechanism. They will not undergoes reaction to the E2 mechanism. This is about the effect of basicity. The second one is effect of size of nucleophile. Size of nucleophile. This is the second one. So nucleophile size, it can be two ways. It can be small or it can be bulkier. If nucleophile size is small, in that case substitution is favorable over elimination. If the nucleophile size is bulkier, in that case elimination is favorable over the substitution. Because like first I will explain about the bulkiness of the nucleophile. So when we have this compound, and we'll take potassium tertiary beta oxide. Okay, so this is the bulky nucleophile. Okay, so first step is the formation of carbocation. The second step, so this is the bulky, it cannot go and take this position like this. So since this is bulky, this cannot take this position. Instead of that, it just abstract a proton from this and eliminate as a tertiary butanol, and this will be forming a alkene product. Okay, that's why when we have a bulkier nucleophile, in that case elimination is favorable over the substitution. If the nucleophile is a small, imagine that nucleophile is a some OH minus. So since this is a small and this gun goes and attacks here, and here in this case the substitution is favorable over the elimination when the size of nucleophile is small. And next we have a effect of temperature. This is very important, effect of temperature. So for this we'll take this principle, delta G equals to del H minus T delta S. So here the temperature is increasing means delta S also increases, right? If temperature increases, delta S also increasing. Okay, now if you will take a substitution reaction in the presence of OH minus, so here we have this one is one alcohol plus leaving group. Okay, and same if we will take elimination reaction for this, we take some base here, and the total products how many we get is this is a 1 and H and X, HX, and then base. So in the first substitution reactions, how many products we are getting here? Two products. Whereas in the second step, elimination reaction, here we are getting a three products. Okay, so we know that if number of products are more, the delta S also more. Okay, this we know. So now from this we can say that if delta S is increasing means temperature also increasing. For elimination reactions, entropy is more. That means at high temperatures, elimination is preferable over substitution. Okay, so this is the thing we need to remember. Effective temperature is at high temperature, elimination is preferable over the substitution. Okay, and further it also depends upon, even if it is a high temperature, like if you want to say E1 and E2 at high temperature, and further we have to see a weak base and strong base concept, and we'll see some of the examples here. So here we have alkene. This is upon treatment with Br. So this Br goes this way, and since this is a positive charge, so this comes and attacks like this. So this will be a Br plus here. Now in the first step is the Br2, the product A comes. In the second step we have a tertiary butanol, here product B comes. Okay, and the mechanism I am writing here. So in the second step we have whatever Br minus is here, that goes and attacks to this. So these reactions are always SN2 reactions. So imagine that this is above the plane and this should be below the plane. Now here we have a tertiary butoxide, is a base here. The base abstracts this hydrogen. So this cannot be a substitution. This has to goes by the elimination only, because base is a bulky here. So this abstract this hydrogen. So then, and the elimination of Br takes place, and here we are getting this compound. And further if we will take one more tertiary butoxide base, and this also get eliminated, and finally we will get this compound. In examination point of view, if they mention excess tertiary butanol, there is a excess, in that case we will get this compound. If only one equivalent, in that case we will get this compound. And here we use a strong base. So since we are using a strong base, this is the E2 elimination, not E1 elimination. Okay, that also we have to see. And then we'll take this example. So this is the base is here, DBU. DBU means 1,8 diaza bicyclo 5,4,0 undecane 7. So this is the DBU IUPAC name. So this reaction is taking place at 80 degrees temperature. Okay, so 80 degree temperature means high temperature. At high temperature, elimination is preferable. Okay, this is not a substitution reaction. And what about the base now? So first we have identified that here elimination is preferable over the substitution. Now we have to identify whether it is a E1 elimination or E2 elimination. So in order to identify whether it is E1 or E2, first we have to know about the what is the role of DBU, whether it is a strong base or weak base, or we can also say it is bulkier base or a normal base. So if we see the structure of DBU, it will be like this. And so this is the bulky base. Okay, so bulky bases prefer for E2 elimination. Bulky as well as strong bases prefer for E2 elimination. Okay, even though here we have like alkyl halide like this. Now here this is alpha and this is the beta. The hydrogen means like at beta position hydrogen is present, so this dbu abstract this hydrogen, and what the product what we'll get here is, so this is the product here we'll get. So just remember that since db is a bulky base, so this it prefer for E2 elimination over the E1 elimination. And the next example we have here, this is another example, and this is also very important example. And here we have iodine. The conditions are dbu in the presence of THF, okay, at a so at 80-degree temperature. So this is the condition. So we know that the high temperature elimination is preferable, and strong base E2 is preferable. Okay, these are the two conditions. And now the point is, so this is a beta and this is also beta, and here we have hydrogens and here also we have a hydrogen. So from where this dbu abstract the proton? So this comes under the regioselectivity. Okay, so when the base is bulky, we know that this is bulky base, this is a structure, this is bulky in nature, the hydrogen will be abstracted from the less hindered side. So this is more hindered side and this is the less hindered side, and the product what we will get here is, so this is the product here we'll get. Okay, since dB is a bulky, it abstracts this hydrogen but not this hydrogen. Okay, and the final conclusion is like okay, and one more example, two more examples I have here. So when we have cyclox means like this compound, this is under in the presence of H3PO4 or H2SO4 or HCl. Okay, and the second step is we have a water at 165 degrees centigrade. So what is the product here? So first thing is we have to identify whether it is a, so this can also undergo substitution reactions. Okay, we have to identify whether it is a elimination or substitution. So we have a high temperature, that means it's a elimination reactions. Okay, and here we have weak base. Water is a weak base, so that is a even elimination reactions. Okay, and here the first step is that these are the protonating agents, the lone pair which is present on the OH. So the proton will be going from these three agent, means like here we can take any one, H3PO4 or H2SO4 or HCl. The proton goes from here to here, and now it will become a OH2 plus. Okay, now since water is a weak base, this abstract is hydrogen, and here we'll get a this compound. Okay, so this is the E1 elimination reactions. And same here we can take another example. In the first step we have PHMgBr and H3O plus. The second step here we have H2SO4 and H2O. So in the first step what we will get? We will get this compound in the first step, OH and pH. In the second step this OH2 plus will come and the elimination will take place, and final product will be this one. So this also undergoes E1 mechanism. Okay, so the final conclusion is like this: tertiary carbocations, allylic carbocations, benzylic carbocations, alpha heterocarbocations. Okay, this all undergoes even elimination reactions, because even elimination is one another thing we need to remember. For even elimination reactions, stability of carbocation is very important. Okay, so this all undergoes even elimination, and this all also can undergoes U2 elimination in the presence of strong base. Okay, this is very important. So these stable carbocations undergoes reaction through the E1 as well as E2. In the case of E2, we need a strong base. Now the secondary and primary carbocations, they undergoes reaction through E2 but not by the E1. Okay, this is also very important. So primary secondary carbocation, they undergoes reaction only through the E2 elimination but not E1 elimination, because for E2 elimination we require a strong base. Okay, so that's why it's going on. For E1 elimination, the stability of carbocation is matter, but since these are not stable carbocations, so these cannot undergoes E1 elimination, they can only undergoes E2 elimination. And here we have one last example. OH. Here we have a methyl group. So in the first step we have a reaction with tosyl alcohol, and the second step we have a water. Okay, so we know that it's even elimination reactions because we have weak base, and the stability of carbocation also, it is a more stable. Okay, so in the first step, this will gets converts into OTS. Upon elimination of OTS, it's a good leaving group. This will become plus add methyl group, and this hydrogen, like here two possibilities are there. The water can abstract whether this hydrogen or this hydrogen. Since this is a hindered side, water can take this hydrogen because it's a less hindered side. We'll get this compound. Here we have this compound. And what about the norbornene? So whether in norbornene case elimination is happens or no. So in order to the elimination reaction takes place, the carbocation which is forming, that should be attain a planar structure. But when we will take a norbornene system, if you do protonation here, in that case this will not attain a planar structure. This is not a planar structure. So because of that reason, in case of these compounds, elimination is completely ruled out. Okay, so there is a rule called Brecht's rule. So according to the Brecht's rule, so this will not attain a planar, it will not get a planar configuration. So because of that reason, elimination reactions are not favorable in this case. So next effect is a solvent effect. So polar solvents and non-polar solvents. Polar solvents prefer for even elimination, and non-polar solvents prefer for U2 elimination. Why polar solvents prefer for even elimination? Because polar solvents forms charge species. Okay, and non-polar solvent will not form a charge species. So as we know that in case of even elimination, the first step forms a charge species. Because of that reason, like if we will take a H3PO4, H2SO4 and HCl, So they are forming a charged species in the first step. And whatever the elimination reactions I have explained before, heat elimination, there we have taken solvent as acetone. Because they are non-polar solvent, they will not form say any anions, sorry, any carbocations. For even elimination, we need to generate a charged species. Because of that, we will use a polar solvent. For heat elimination, we don't need to generate any charged species. But because of that reason, we are using a non-polar solvents. Then last effect is a effect of leaving group. So here we can't say like if a good leaving group is there, then this elimination reaction is possible. Bad leaving group is there, this elimination reaction is possible. That we cannot say here. Like in case of substitution reaction, if good nucleophile is good leaving group is there, their SN1 will be favorable. If bad leaving group is there, SN2 is preferable. Like that we can say. But in case of elimination, if good leaving group is there, then rate of reaction will be faster. If bad leaving group is there, then rate of reaction will be slower. This much only. And here we have an example, NME2. So this is appointed with methyl iodide in the first step and KOH in the second step. So just remember always OH and NH2, NME2, so and OME, these are not good leaving groups, these are bad leaving groups. But we can make them as a good leaving group by making a OMe H plus or OH2 plus and NH3 plus and Me3 plus. So in this form, these are good leaving groups. So for that, we have a methyl iodide plus here, the lone pair which is present on the hydrogen, abstract this methyl group, and then we have a NME3 plus. So now we just converted this compound, this group from the bad leaving group to the good leaving group. So next the elimination will takes place, and the KOH is the strong base. So because of the KOH is strong base, here the reaction what takes place is a E2 elimination reactions. So this is the final product here we'll get. And then this is the starting precursor in the presence of water and heating. So we know that water is a weak base. Weak bases prefer for even elimination, right? So that means this eliminates. This is the product here. So next last